what we're talking about, remember, is this thing called related rates. And the idea is pretty simple, right? You have the idea is like this: a relation between quantities yields a relation between their rates of change. Okay, and so last time we started off with this example, right? Somebody, you have a square, given a square whose diagonal is increasing at a rate of something, right? It was 2 centimeters per second, let's say. How fast is the area changing when the diagonal is 5 centimeters. How fast is the area changing when the diagonal is 5 centimeters? And so this is how the problem is stated in the book. And if you were given this problem, then the first thing you would do is say, well, let's put some variables on it. Right? Maybe we'll call the length of the diagonal. We'll call that length of diagonal at time t. Right? And we'll call A of t the area of the square at time t. Right, so put some names on things, and then rephrase your question. Right, maybe you can restate what you've been given. Right, what are you given? You're given that the diagonal is increasing at a rate of 2 centimeters per second. Right, so that says that the rate of change of the diagonal is 2 centimeters per second. Right, the derivative of that is 2. Right, and the question is how fast is the area changing? So the question is, what is A prime? What is A prime when d equals 5? Right. So name. You do some naming and you rephrase. You rewrite the question. Now, what you need, of course, is a relation. Right? They're asking you for the rate of change of A, and you're given the rate of change of D. Right? So, what you look for is a relation between. So we need. We need a relation between A and D. Right? We need a relation between A and D, and if we can find a relation between them, we differentiate it. We'll get a relation between A prime and D prime, and then we'll use the things that we're given, D prime and D, to figure out A prime. Okay. Right? So we need a relation between the area and the diagonal. Right? So if you know what the diagonal is, do you know what the area is? Right? If you know what the diagonal is, do you know what the area is? Right? And so we already gave it to you last time, but can anyone see immediately a relation between diagonal and area? Yeah. Okay.
So if we just called one of the sides of the square would be d over root 2.
D over root 2. Okay. Yep.
And then the
That's
square
here.
would be just, yeah.
Yeah, and so then the area is going to be d squared over 2. Right? So you just use the Pythagorean theorem, and that gives it to you, right? So some geometric thinking yields that area A is d squared over 2. Okay. This is actually a famous question. Is there a relation between the area and the diagonal? It occurs in Plato's one of Plato's dialogues, Meno, where Socrates tries to show that everybody has some inherent knowledge, and he calls a random slave boy up, and he starts battering him with questions, and he eventually makes the slave realize that eventually the boy, who has no education, is able to say that, well, look, if I had a square, then what I see is that d squared is this area, right? D squared is this area, which happens to be twice the original area. Right? Yeah. So d squared is twice the original area. Anyway, is that right? Am I saying it wrong?
Yeah.
Okay. Yeah. Okay. So then from here you'd say, okay, well then you differentiate that, and you get A is 2d prime over 2. In other words, dd prime. Right. It's going to be dd prime, and so I'm sorry, A prime. A prime is dd prime, and so you can answer your question: what is A prime? What is A prime when d is 5? What is A prime when d is 5? A prime is going to be 5 times 2 centimeters squared per second. Okay. And so this is what we did last time, although I'm making it a little bit more formal, laying out the procedure more clearly this time. Okay, yeah, go ahead.
Where is that 2 from?
That 2, remember, so we've got A from here. We know that A is equal to d squared over 2, so A prime equals d prime.
Mm-hmm.
So this is your relation between the rates. A prime, the rate of change of A prime, the rate of change of A is the diagonal times the rate of change of D.
Right.
Right? Well, we're given that the rate of change of D is 2. And the question is, what is the rate of change when diagonal is 5? So it's going to be 5 times 2, 5 centimeters times 2 centimeters per second.
Okay.
So you get 10. At that point in time, the rate of change is 10 centimeters squared per second. Yeah, tell me.
When you take the derivative of a of t, don't you have to square the bottom, so a over 4?
Here,
Yeah.
you're differentiating this. So this is, A is a constant times d squared,
Oh, okay.
right? A is a constant times d squared. So you're not really using you don't use the quotient rule, but just the fact that the derivative of some number times something is just that number times the derivative.
Okay.
Yeah, I mean, if you could use the quotient rule, it would work out if you use the quotient rule. Right? If you differentiated this, what do you get? Well, you get the bottom times the derivative of the top minus the top times the derivative of the bottom, which is 0, over the bottom square. Right? So you get the same thing. But nobody would do it this way. Okay. But it's perfectly legitimate too. Okay, so let's do more examples. So case 1, air is pumped into a balloon, into a spherical balloon. So this balloon is somehow rigged so that it's always a perfect sphere, so that its volume increases at a rate of 100 centimeters cubed per second. How fast is the radius changing when the diameter is 50 centimeters? How fast is the radius changing? The diameter is 50 centimeters. Okay. So maybe let's do this one together. What kind of things should we put names on? What names should we use? Yeah. Okay.
Volume.
Volume.
Could
Okay.
be V of t.
So volume, we're going to call it V of t.
And radius.
Well, the radius at time t.
And that, should we do diameter?
Not really. I guess we don't, because radius is just twice diameter. You could. Right?
Okay. Yeah,
But
yeah.
radius is just twice. I mean, I say diameter is twice radius. So you don't really need to create another one. Yeah, Victor.
Is the time t always 100 centimeters?
Yeah. So what you're given. So let's rewrite the question. You know that v prime of t is always 100 centimeters cubed per second, right? And the question is, what is r prime t when the diameter when 2r, so when r equals 25. Okay. Right. And so you look at it, you say, okay, these are the two things that I need. I'm looking, I'm given this rate of change. I want this rate of change. So I want to find a relation between V and R. Right. What's the relation between V and R? Does anyone remember this? Okay, go ahead.
4/3 pi r cubed.
4/3 pi r cubed, yeah. So the volume of the sphere is 4/3 pi r cubed. Right. Right. And so you differentiate that, and you get V prime is equal to 4 pi r squared r prime.
Could you explain
That is the chain rule, right? So you have, right, 4/3 pi r cubed, right? So 4/3 pi is just a constant, right? So that doesn't affect anything. When you differentiate that, you're going to get 4/3 pi times the derivative of r, this function cubed. Right? So here's some function cubed. What's the derivative with respect to t of this? 3, whatever it is, squared times. So we're using the chain rule, right? You differentiate the outside guy, evaluate it at the inside guy, then When? Yeah, multiply by the derivative of the inside out. So you're gonna get 3r squared r prime. So 3r squared r prime, so it becomes 4 pi r squared r prime. Okay, so that's what we have here. Okay. So you have a relation between the rates. You have this relation between the rates of change. V prime is equal to 4 pi r squared r prime. Right. Okay, and then you need to solve for r prime, and that's just a matter of plugging in information. Right? So you have 100 is equal to 4 pi r. R was 25 centimeters. I'm just going to get rid of units. 25 squared. Right. And so you've got, what do you end up with? You end up with r prime, there's 100 there, there's 100 there, there's 25 there, 25 is down, oops, 25. And the units work out to be centimeters per second. Okay. So when the balloon is 100 centimeters across, I'm sorry, when the balloon is 50 centimeters across, right? Then the rate of change of the radius is yes.
So would you be able to say then that like the r prime is 1 over r pi?
Yes. So I mean, what you can say,
Yeah.
what we have here is that here's this relation between the rates of change, right? That you have 1 over pi, 4 pi r squared v prime, right? So, right, if the rate of change, if the rate of the change of the volume is constant, right? Here we have this thing, the rate of change of the volume is constant. There's a pump that's pumping at a constant rate, right? And what this is saying is that as the balloon gets bigger, the rate of the change of the radius decreases like an inverse square, right? Because at the beginning, when the air is going in, the balloon is tiny, and so the rate of change is going to be huge, right? Right? When your balloon is 1 millimeter in radius, say, then the rate of change of its radius is going to be dramatic, right? Because the pump is going at a constant rate, right? But when your balloon is gigantic and you're pumping in still the same amount, well, the radius is going to be changing quite little, and you see that the relation is this inverse square relation. So that's pretty cool, right? This inverse square shows up here. There's a very precise relation between the two rates. Okay. Okay. How do people feel about it? Do you want to see, like, how many more examples do you want to see?
At least one.
At least 1, 2, 3? Close your eyes for a second. How do you feel? We're definitely going to do one example. Should we do 2 examples? Raise a finger if you want to see 2 examples. Okay, put your hands down. Okay, thank you. Open your eyes.
Are they always geometric, like circles and boards?
Yeah, I mean, these problems, in order to make them doable, there's usually some geometry involved, so you can figure out the relation between the two things. Yeah, I'm afraid so. Some geometry or trigonometry. So we'll do one example that's geometric and one example that's trigonometric. Okay. So you have a cone. So I'll let you do this one. You have a cone whose height is decreasing at a rate of -4 centimeters per minute. And further, you have that its radius is increasing at a rate of 6 centimeters per minute. Okay. So the height is shrinking and the radius is increasing. Okay. When the question is, when R is 9 and H 12, how fast is the volume changing? How fast is the volume changing? Oh, yes, Stefan.
Do we need to know the formulas for volume?
You do. So does anyone remember it? The volume in terms of height and radius?
No.
That's okay.
What's 1/3?
I R squared H. Okay. 1/3 the volume of a cylinder with those dimensions.
Okay. Should we know the volume for like most shapes, like sphere, cone?
In some sense, yes, you should. Right. Like I hope you've seen it before. It'd be ideal if you remembered it. But if you're asking, like, do I expect you to know that? Do I expect you to have that in your brain? Well, not necessarily.
So we don't need to know for the quiz. Like,
No.
we get to know it, but
Yeah, I guess for. Let me think about the answer.
okay.
Yeah, these things I think you probably should know just because they're basic, but maybe you don't. And it's Anyway, let me think about that. Yeah, so work for say 1 minute and set up what you need to do. Should not take more than a minute. To at least set it up.
Oh.
You should be pretty close after 1 minute, right? Yeah, to be honest. Okay, turn to somebody nearby and say what you're doing.
So what I did is I used the derivative of that, which is RT. I think I used the 1/3 pi, which I guess it would be very appropriate into my first thing to because it's
Since it's R squared.
but I don't really know what to do with the 1/3 pi. Like should I multiply the whole my
So
product
it'd be
rule answer for R
R squared H.
squared.
R
H
squared
T
H prime
times that,
times
or should I distinguish with
H
this?
is 2R
Okay. Would somebody like to tell how to do it? Like somebody would want to say how to do it? Except for Claire.
I just have a question.
You have a question? Okay, go ahead.
So when you're doing the derivative,
Mhm.
what do you do with the 1/3 pi? Do you incorporate that into the first product, or do
You could.
or can you multiply that whole thing, or 1/3 pi by the whole product
Sure.
of r squared?
Sure.
So,
So-
either way, fine.
Yeah.
Okay.
So you have these rules, right? The derivative of a constant times a function is that constant times the derivative of the function.
Yeah.
Right? So here's a constant. You can just pull the constant out, plot it on the side.
Uh-huh.
Yeah, you could say, when I differentiate this, v prime is going to be 1/3 pi
Uh-huh.
times the derivative of r squared h.
Okay.
Right? You can pull the constant out.
Uh-huh.
Right? Or you can use the product. You could say, I'm gonna think of this thing as one function.
Okay.
Right? And I'm going to say, then I take the first guy times the derivative of the second, plus the second guy times the derivative of the first. The 1/3 pi is still going to persist there, so you're going to get it in each term anyway,
Okay.
right? So
Either way.
yeah, you'll get the same answer either way. So so v equals 1/3 pi r squared h, right? R is a function of time. H is also a function of time. H is also a function of time, right? And so what do you get when you differentiate? It's the same people. It's the same people. I'm gonna choose somebody at random. Asha. Just look up. That's a great expression. What do you get?
1/3 pi times 2RH plus r squared
2RH plus r squared. So how did you get that?
the product rule.
The product rule. So you take the, so these guys are both functions, right? So you take the first guy times the derivative of the second guy, and so that should be h prime, right? And then the derivative of the first guy, what's the derivative of r squared?
2r.
2r,
Another h.
so you've got r squared and you differentiate it, you're going to get 2r
Times the derivative.
times r prime. So you gotta use the chain rule, right? Chain rule, 2r prime, so derivative of the first guy times the second guy. Okay, so v prime is 1/3 pi r squared h prime plus 2r r prime h. Right. Okay, so I just wrote it again. So, and then you just plug things in, right? How fast is the volume changing at that point? Well, r squared, so you get this r squared times h prime plus 2r r prime times h. Right, so you just plug in numbers, and then whatever that is your answer. Yes.
Should we be able to multiply that by hand?
Yeah, why not?
Maybe, yeah.
I mean, yeah, why no?
Okay.
I mean, but that's not the point of the course. certainly I expect you to be able to multiply numbers, right?
Yes.
Like it's something that you did. So certainly you should be able to multiply numbers, right? That's just an elementary school ability, right? Now as for whether or not I'm going to ask you to multiply numbers, I'm not going to ask you to multiply numbers.
Okay, because it's more important that we know how to set it up.
Yes. I mean, because once you get to this point, what's left to be done? Just multiplying numbers,
Yeah.
which is something you can do.
Oh.
Yeah. So, but yes, you should be able to multiply numbers.
Yes.
Sorry,
Yeah.
that's what I meant when I said yes, of course.
Okay.
But maybe that's sort of obvious. Okay. Okay. So, any questions? Any questions? Let me do. Mercedes?
Sorry.
Something good happened, or no? You figure something out?
I was trying to actually solve it, but I'm like, no.
Yeah, it's kind of a pain, right? Because you have the 108, right? So you have the 54 times 2 is 108. Well, that's not so bad. It's 1296, right? 1296 minus 324, right? So that's 900 and like 72. Right? Which is 324. Yeah, so it actually is not that bad. Yeah, but that's nothing impressive. The real king of mathematical tricks is Art Benjamin in Harvey Mudd. He's like he's a basically world class mental calculator. So you just like throw things at him, and just whenever you see him, just throw numbers at him and see if you can solve it. Right? The trick of taking square roots, I'm sure he could do much better than what I did. Yeah, apparently, like he was on Stephen Colbert show at one point, just for fun. Okay. Yeah. So last one, I guess. So let's see what the question is. So right. So there is a tower here. There's a tower here, and there is somebody running away from the tower. Okay. And there's a spotlight being shined down from here, from the top of the tower, on this person. So maybe it's like a jailbreak. So this, like, the guards in the tower are shining this light on the people running away. Yeah, previously I had said that it was like somebody fleeing a lover. Previously, I think the setting is that there's a boat actually. In the water. There's this tower, the lighthouse, and the tower. Anyway, in any case, however you want to think about it. Okay, so. And you know that the boat or the people fleeing are traveling at a rate of they're traveling at a constant speed of 300 feet per minute. 300 feet per minute. The tower is 100 feet tall, and you want to know how fast is theta changing. So how fast is this angle changing? So there are 4 minutes left in class. Let's take one of them and see if you can set it up and see what you can get. There should be one more bit of information,
Yeah,
which is
okay.
when the distance is 1,000.
Okay.
When the distance is 1,000 feet away. Okay, so let's work this out. Let's work this out together. Let's put some names on things, right? Theta, of course, is the angle, right? Theta is a function of time, right? And what are we going to call the distance? The distance here.
D.
D. Okay. D again is the distance. Right, that's a function of time, right? And what you're given is that d prime is constant, right? And you want to know theta prime when d is 1,000, right? So again, you need to find a relation between theta and d. Well, what's the relation between theta and d? Tangent, right? You know that the tangent of theta is d over 100, right? And then differentiating that, what do you get? Secant squared. What do you get? Wait, just read it off. Secant squared. So you differentiate the left side, you differentiate the right side. The derivative of the tangent is secant squared, right? So secant squared evaluated the inside line times the derivative of that, and we get d prime over 100. Right? So theta prime is the cosine squared. I'm just going to move this guy to the other side. Cosine squared of theta times d prime t over 100.
Where did you get that?
Wait, yeah.
Secant is 1 over the cosine. Right? Secant squared is the same thing as 1 over the cosine squared. So I'm just going to multiply both sides by cosine squared. Yeah, Stefan.
Could you take the derivative of either side, or do you have to take the derivative of the left side?
You have to take derivatives of both sides, right? Because you have this relation.
Oh.
You differentiate the whole relation.
Okay.
Right. The derivative of the left equals the derivative, right? Okay. So, and then that gives it to you, right? Theta prime is going to be d prime over 100, right? So that's 300 over 100 times the cosine squared of the angle at that point in time, right? And you can figure out what the cosine is, right? It'll be the adjacent over the hypotenuse. Right? So that's going to be, cosine is going to be the adjacent over the hypotenuse squared. So that's it. Okay. Cosine is going to be the adjacent over the hypotenuse. So you get that thing squared times 300 over 100. Okay. Okay. Okay, so that's it. This is sort of a nice application of